Welcome to this explainer. If you're the kind of person who just loves figuring out exactly how the world around you actually works, you are definitely in the right place. Today, we're going on a really fascinating journey. We're going to start way down at the microscopic level with a tiny component called a light-dependent resistor. It's a sensor that costs literally just a few pennies. And from there, we'll trace its logic all the way up to massive, high-voltage smart city infrastructure. By the end of our time together, you're going to understand exactly how automated streetlights somehow just know when the sun goes down, and how engineers build these amazing systems from the ground up.
Okay, let's dive right into this. Here is the blueprint for exactly how we'll get there. First, we'll look at the energy waste problem. Then, hardware and sensor physics, wiring the voltage divider, writing the smart code, looking at day versus night output, and finally, scaling it all up to smart cities.
Let's kick things off with Section 1, the energy waste problem.
To understand why we even need these smart systems, we really have to look at the glaring inefficiencies of the old ones. Traditional streetlights, they often just rely on simple mechanical clocks. They're programmed to run on fixed schedules, say 12 hours straight, completely ignoring what's actually happening up in the sky. This means that during those bright summer evenings, or twilight hours, or just unseasonably clear days, massive amounts of municipal grid energy are completely wasted. We're talking about wasted electricity that can cost major cities millions of dollars a year, literally just lighting up streets that don't need to be lit. What we desperately need here is a dynamic, automated feedback loop, something that samples the actual ambient light in real time.
And that brings us to Section 2, Hardware and Sensor Physics.
Now, what's really interesting here is the pure, almost binary physics of the semiconductor we're using. It's called a light-dependent resistor, or LDR for short. During the daytime, in bright light, photons literally bombard the material, which liberates free electrons. This sudden burst of activity increases conductivity, causing the electrical resistance to plummet down to just a few hundred ohms. But in darkness, the exact opposite happens. Without those exciting photons hitting it, the free electrons just recombine, and the resistance? It spikes dramatically into the mega-ohm spectrum. So the ambient light level physically dictates the electrical resistance of this tiny component. It's pretty amazing when you think about it.
Moving right along to Section 3, wiring the voltage divider.
So we have a sensor that changes its physical resistance. Great, but here's the catch. A microcontroller like an Arduino can't read raw resistance directly. It needs a translator. Enter the voltage divider network. You can think of it kind of like an electrical tug-of-war. By pairing our changing LDR with a static 10 kilo-ohm resistor, we create a circuit that dynamically shifts the voltage drop as the light changes. One side pulls harder as its resistance goes up. Now, the Arduino has a built-in analog-to-digital converter, or ADC. This ADC reads that fluctuating electrical tug-of-war and translates it into a clean digital number ranging from 0 to 1023. Bam! We've successfully bridged the gap between invisible physical resistance and a digital value our code can actually use.
So, how do we physically wire up this interface? Let's map it out. We pull 5 volts from the Arduino's power rail directly to one leg of the LDR. The real magic happens at the other leg, which actually splits. One path goes to our analog input pin A0 to be read by the brain, and the other path routes right through that 10 kilo-ohm resistor down to the ground rail, pulling the voltage down. Finally, we connect digital pin 13 to our street LED's positive anode and route the LED's negative cathode back to ground. And just like that, our physical prototype is fully built.
All right, next up is Section 4, writing the smart code. Our hardware is all wired up, but without software, it's really just a bunch of idle copper and silicon, right? We need to give it a brain. Let's move to the software and see how this builds a complete logic loop inside our C++ Arduino program. We're essentially following a simple recipe here. Step 1, we define our hardware pins so the code knows exactly where to look. Step 2, we establish our state threshold. We just pick a number, say 400, that represents our ideal darkness level. Step 3, we open up a communication pipeline to our laptop so we can actively monitor the data stream. Step 4, we continuously acquire that analog input from the sensor. And finally, Step 5, we evaluate conditional logic. Based on the digital number we're receiving, the brain decides what action to take.
And here is the absolute core of that decision-making process. It's a remarkably simple if-else statement. If the incoming ambient light level falls below our predefined darkness threshold, well, the system uses the digital write command to push pin 13 to high. That turns the street light on. Conversely, if the light level is above the threshold, it drives the pin low, shutting the light off. The microcontroller is executing this check every 250 milliseconds. It's constantly sampling the environment, reacting almost instantly to passing clouds or a setting sun.
Let's see this logic in action in Section 5, Day versus Night Output.
What actually happens when we upload this code to the ATmega328P microcontroller in the real world? Well, let's walk through scenario A. Daylight. The sun is shining brightly on the sensor, the resistance drops, and the Arduino reads a high value, let's say 750. Because 750 is strictly greater than our 400 threshold, the Arduino's response is to drive the pin low. The physical output, the street light stays completely off. But fast forward to scenario B. Nighttime. The sun sets, resistance spikes. The Arduino reads a plummeting value, say 185. Since 185 is much less than 400, that condition triggers, the pin goes high, and the street LED physically turns on instantly.
Now, while this is happening physically out on the street, engineers can actually monitor the system digitally. They use a diagnostic stream running at a 9600 baud rate. If you were looking at the screen, you'd see a text stream updating continuously, saying something like, "Status nighttime, streetlight latch energized." This serial stream is absolutely crucial. It's what allows engineers to debug the system and perfectly calibrate that light sensitivity threshold based on the specific ambient light of wherever the system is deployed.
Finally, we arrive at Section 6, Scaling to Smart Cities.
We've built this tiny 5-volt prototype on a desk, but we have to ask the big, so what question, right? How does this actually impact the real world? Well, these exact principles are deployed absolutely everywhere today. They're replacing those outdated mechanical clocks on municipal highways and urban roads, meaning they can dynamically turn the lights on earlier if a massive storm rolls in and causes dark, overcast skies. They are used on smart corporate and university campuses to safely illuminate walking paths. They drive residential landscaping accents. They're even utterly critical for remote, off-grid solar lighting stations, where conserving battery power by only turning the LEDs on when it is absolutely necessary is literally a matter of system survival.
So, the crucial point is how do engineers safely scale our little 5-volt prototype to handle dangerous, high-voltage city grids? It comes down to 3 main things. First, they use electromechanical or solid-state relays. Think of these as heavy-duty bridges. They allow our safe, low-voltage 5-volt logic pin to trigger a massive switch that controls those intense 230-volt AC industrial LED arrays. Second, they write debouncing filters into the software. These are brilliant little time-averaging delays. They prevent the streetlight from accidentally shutting off just because a passing car's bright headlights temporarily flashed across the sensor. And finally, they attach IoT mesh transceivers. These incredible network chips connect thousands of streetlights into one central grid, automatically alerting maintenance crews the second a specific bulb burns out. It's a total game changer.
We've gone all the way from a single photon hitting a tiny resistor up to a fully networked, self-reporting smart city grid. Understanding this underlying logic completely changes how you look at the infrastructure around you, doesn't it? It really makes you wonder, as these sensors and microcontrollers get cheaper and more powerful every single day, what other dumb infrastructure in your neighborhood is just waiting for a smart, sensor-driven revolution? Keep an eye out, because the connected world is only getting smarter. Thanks for joining me for this explainer, and keep learning.